Welcome, crew. I'm going to try to talk quickly so that I don't go over my YouTube 15-minute quota. But we're talking about the fundamental theorem of algebra. What the heck is this? Well, this talks about how if you have a polynomial function, so let's say that you have this very familiar guy, right? That you have at least one solution to it that you can actually solve for. Well, what do I mean by that? Because you might be wondering, well, this, you've told us that you really have as many solutions as that power. So what the heck do you mean, like, at least one solution? Well, that's where the corollary, in other words, the addition to the fundamental theorem of algebra comes in, which is that all polynomial functions have at least one root that you can solve for, but it may count more than once. This is where multiplicity comes in. So yeah, technically, really, this function, for example, has only like one real root there, but it counts twice, right? This is multiplicity of 2, right? Now, that is not to say that my at least one solution that I can find from this guy has to be real. I could have some function up here, right? X squared plus, I don't know, 9. So it doesn't have to cross the x-axis. In this case, well, though, what do you have? You have a complex solution, and that's where the complex conjugate theorem is going to come in for us as well, where I'm not saying that this is a solution for this guy, but let's say that if this was one of the roots, you know that the complex conjugate also has to be a root for that polynomial function. Now this also counts for just plain old roots. It doesn't have to be imaginary. What if I'm telling you that this is a solution? Well, its partner is also going to be a root. Notice how I treated it just like a complex conjugate in the imaginary numbers example, and that I changed the sign in front of the root. And why do I say in front of the root? Because I is technically a root. You know that by definition, I is the square root of -1. Okay, so we've talked at length about the definition, but how does this look in examples? Well, you've had a lot of stuff on your homework, let's say, where I tell you that, okay, let's say that this is a root. Those are the roots of a polynomial function, and I'm asking you to find the simplest function for that. Well, you know that you are forced to say that if this is a root, that his partner is also there. Now, I'm asking for the simplest polynomial function, so don't go adding more roots if you don't have to. You have to if these are square roots, but on your quizzes, I've seen a lot of y'all actually put like, oh, well, if 2 is a root, -2 must also be a root. And that is not so. I'm asking for simplest. So how are you complicating things by doing that? Well, if I had told you, ignoring this part, let's say that I told you that you had a root there, the simplest polynomial function that could go through 2 would just be a line, right? But if you go adding more complexity to this and saying like, oh, well, if 2 is a root, -2 must also be a root, well, now you're not being simple, you're making this a more complicated function. You're making it a quadratic at least. So don't go adding complexity if you don't have to. I'm asking for simplest polynomial function. So if I gave you a real root, that can stand alone. Now you are forced, though, to now have to FOIL something like this. Now, for purposes of length of this video, I don't really want to go into proving how the trick that I'm about to show you would actually work if I tried to FOIL this out, which it will, but I don't want you to focus on that for now. What I want you to focus on is the rational root theorem and knowing that if you have a root or an imaginary number, you're going to have its complex conjugate. So how do I avoid having to FOIL all this mess and still find the simplest polynomial function for these three roots? Well, what I can do is I can actually go back to my roots, add them, multiply them, and stick them into the following quadratic polynomial, and I'll have actually FOILed. Now, it's a fun proof to do by yourself later if you want to actually FOIL this and prove that you will indeed be able to get this formula by just plugging in. It's a fun proof if you want to prove it to yourself. Just know that I don't expect you to actually do that by hand. Now, if you actually FOIL this out, you get 1 minus root 3 plus root 3 minus the square root of 9, right? Why am I explicitly saying that? Because a lot of y'all were saying that root 3 times negative root 3 was negative 9. Don't forget that root there. These guys cancel, so you get 1 minus square root of 9 is 3, and you get negative 2. Plugging into this polynomial trick, you see that this is going to be x squared minus 2, because you get a minus a, right? X plus m. You still have that x minus 2 from this guy that you're not forgetting. And then, unfortunately, you do still have to FOIL this guy. So you're going to go x cubed minus 2x squared minus 2x minus 2x squared plus 4x and plus 4. Now, hopefully I've done good mental math here. When I combine these guys, I get negative 4x squared. These guys, and I get plus 2x plus 4. Notice how I still put it in the standard form, in other words, decreasing power order. So this is a more complex example, but let's go into something a little bit more complicated. So let's say that I gave you a root that looked like that, and I said, okay, give me the simplest polynomial function for the following root. Well, you know from what I've just told you that this guy, his complex conjugate, would also have to be a solution. So again, I'm going to employ my trick. Go back to the roots, add them. Notice that the imaginaries cancel, which is nice, that's what's supposed to happen. But this doesn't go away, and adding doesn't end up giving you 0. A lot of y'all think that by employing this trick, what I'm trying to do is actually get rid of all the numbers. It's not. What I'm trying to do is get rid of all the i's. So in fact, if you have i's or roots in your final answer, then you know that you have actually done something wrong. Because complex conjugates get rid of that, right? So, negative 9i squared, these guys cancel, and this is where you do have to remember that I squared is equal to negative 1 back from our complex conjugate days, or our complex algebra days. So that would mean that this is negative 9 times a negative 1, so plus 9, so 13. So what happened? It added to 4, it multiplied to negative 13, so the simplest polynomial for this pair of roots is going to be x squared minus 4x plus 13. Now, I saw this mistake on y'all's quizzes. If I told you to add a root that was 0 to this, right, x is equal to 0, what the heck would the factor to that look like? Well, this is the factor. What you set equal to 0 is the factor. So if you recall, if you had actually been working backwards and had just come from factoring something like this, you would have just had an x in front, right? So whenever you see 0 as a root, that means there's an extra x factor. You're going to go ahead and multiply this in. Hope that Simon Powell doesn't show up, because it's the x factor. Okay. And I'm in standard form. This is my simplest polynomial function. Alright, really quick word. If you have something like a square root of 5, please don't freak out. There is a root there, so he does have a partner. Right? If you say something like just 3i, that means that negative 3i is also there. So very quickly, this would add to 0, this would multiply to a negative 9i squared, which means you would have 9. This would add to 0 and multiply to a negative 5. Be careful when you are plugging into that trick polynomial. This term in the middle goes away, right? Because you have minus 0x plus, minus 5, there we go. So this is your simplest polynomial for these pairs. And this is your simplest polynomial for the complex pairs. It would then be up to you to FOIL this. Ah, 45. And get standard form. Alright, I think I've covered all bases. Good luck on your test, you guys.